Hi, welcome to the 15th session on group theory. Today we will start with some abstract results about group homomorphisms and make use of them to give applications, look at examples, etc. Alright, okay. This is the 15th session on group theory and second session on group homomorphism, just for record's sake. So let F and G, sorry, G and H be groups. Okay, F a group homomorphism. Right? Then just for the time being, usually I don't recommend. For the time being, let EG denote the identity element of G and EH denote the identity element of H. Later I will use only E. Context should make it clear. For example, when I write f of E, this E should be in G and this object should be in H. Right? Because all of us are intelligent, so I don't know to keep writing this unnecessarily. For the time being, I will do that though. So I can ask, what is f of EH? EG. We had already seen in the earlier examples, it's actually the identity element of the codomain. Okay, let us just check it. So the only defining property, one of the defining properties, EG equal to EG dot EG, that is EG squared, right? Therefore, f of EG equal to f of EG times EG, but that's because it's a group homomorphism. This is the binary operation acting on these two elements. Therefore, it's really f of Eg into f of Eg. Now, this is an equation. Okay, call this as B. Therefore, it says B equal to B T times B, where B is E of G, f of E of G. Where does it live? It lives in H, right? So, if I now H is a group, therefore I can apply multiplicative inverse of, sorry, the inverse of B. That is B into B inverse. But this is identity of H. This is going to be into identity of H into B, therefore B. Therefore, we conclude B, which is f of Eg, is EH. That is, a group homomorphism maps the identity element of the domain group to the identity element of the codomain group. So loosely, it maps the identity element to identity element. Okay. So pause, review, proceed. I think my pen, I'm out to change it. It's not doing right. Okay, that's the first result. And second result is start with an A in G. Okay, and let us look at f of A inverse. I want to know what it is. How is it related to f of A? Remember, these are all elements in H now, right? How do I find it? Again, the only way I know about A and A inverse is its identity. Now I will not use EG, but okay, I will write E instead of EG, I will write only E equal to A into A inverse. Therefore, f of E must be equal to f of A into A inverse, but that's equal to f of A into f of A inverse, right? But we know f of E is E. This E is EH. Okay, just for the time being, I will keep writing. Okay, this. Therefore, what does it say? Therefore, f of A inverse is nothing other than f of A inverse, the inverse of this element. If you want to call f of A equal to B, then f of A inverse is B inverse. That is the inverse of f of a, right? So please understand P or P. The third result we need is, suppose A is an element of the group, n is an integer. To start with, let us assume n is natural number. I want to know what is f of a power n, right? It's obvious. We will do induction. F of a is of course f of a squared. By definition, what is a squared? F of a times a. But group homomorphism, therefore it's f of a times f of a. Therefore f of a squared is f of a whole squared, right? So by induction, assume, as induction hypothesis, assume for n in n, f of a power n, okay, for some fixed, okay, we have proved up to 1 to n is f of a whole power n, right? Now let's look at it, f of a plus n. This is a plus 1. Again, what is this by definition? A power n is f of a power n into a. Now these are the two elements of the group G, the binary operation. Therefore it's f of a power n into f of a. But by induction, f of a power n is f of a whole power n into f of a. Therefore it's f of a whole power n plus 1. Therefore we have proved for every natural number n, okay, f of a power n is f of a whole power n. Okay, pause, review, proceed. Yeah, but what happens if n is negative? Suppose, okay, my n equal to minus m, where m is a natural number. Notice that when n equal to 0, I don't know to prove anything, because f of a power 0 will be f of identity, that we know is f of a power 0, which is identity power 0, which is again identity. Okay, for n equal to 0, the result is obvious, because f of a power 0 means f of eg. Okay, right? And f of a whole power 0 will be, remember my, right, f, that will be f of a power 0, that is identity, because for any group element this is identity, right? Call this as b power 0 by definition is the identity element. So result is true for n equal to 0. Now I want to look at what is f of a power n, right? Remember this object, okay, a power n, which is a power n, which is a power minus m. What is our definition of this? It is a power m inverse. Okay, this is by definition. Okay, I hope all of you remember law of exponents. Okay, in a monoid we proved this result. Okay, therefore this is f of am and inverse. But in the last result we proved f of x inverse is f of x inverse. Therefore this is going to be f of a power m inverse, right? But f of a power m is a natural number. For that we know it is f of a whole power m and then the inverse. Call this as b. Therefore b power m inverse by definition is b power minus m, that is b power n. Therefore it is f of a power n. Okay, for even if n is, therefore for all n integers we proved, and for any group element, for every group element we proved f of a power n is f of a whole power n. Okay, pause, review, proceed. I hope all the proofs are easy. Yeah, so please go through that. Okay, next what we want to do is we want to give, yes, hi, there was a disruption. Let us continue. So let us look at some application. So suppose f g to h, a homomorphism between groups, right? And suppose I take an element A in G and assume it's of finite order. Yeah, okay. G may not be finite, but A is of finite order. Okay, order of A is n. Then what do I know? F of A power n is f of E, and therefore this is E. This E is EG, identity of G. This is identity of H. Okay. But what is this? A power n, since order of A is n, f of A power n is f of E. Oh, sorry, that I did. Sorry. F of A power n beside is f of A whole power n is identity. So if I call B as f of A, what it said is B power n is identity. So what is the first observation I can have? Therefore, we conclude B is of finite order. B equal to f of A is of finite order. If A is of finite order, then B is of finite order. Is this statement clear? Right? We can say something more, because B power n is equal to identity. Therefore, order of B must be a divisor of n. Okay? Not only B is of finite order, but order of B must be that is order of f of A must be a divisor of n. Okay? Is that clear? Okay. Now we will give an application of this. This is an application of application. Okay. Suppose I have something, let us say additive group Z2 plus and additive group Z7 plus. Okay, under addition. I want to know, suppose F is a group homomorphism. Okay, I want to understand. Okay, this. I want to make use of the Euler result. What will be your choice of A then? An obvious choice. I am sure all of you will check F of 1. Right? Then what is order of A? Is 12, because 1 plus 1, 12 times 1 is 0, and nothing short of that will be 0, right? Order of A. Now suppose f of A is an element B in Z7, right? Therefore what do I know? Okay, therefore 12 must divide, let us look at order of B, right? Now what are the possibilities? If B is identity, that is 0 in 7, okay, this is an element of Z7, then f of Ka is f of A plus f of A, which is 0. This is the 0 in 7, okay? K times that will be 0, right? For every K. But remember, Z12 is 0, A that is 1, and 2, this is A, this is 2A, and 11A. Okay, that means for every element G in Z12, I have f of G is 0 in Z7. That means F is a trivial, therefore F is trivial homomorphism. Pause, review, proceed. That is where in the case when f of A is 0. You understand? We will assume f of A is B is 0. In that case, F must be the trivial homomorphism. Now suppose f of A is B and B is not 0 in Z7. Okay, it's not the 0 element of Z7. It's not the additive identity. Right? Okay. Then what do I know? Order of B I have to look at. Now B is non-zero element, then we know this Z7 is a cyclic group with every non-identity element is generated. That is order of B is also 7. Because B is not 0, therefore order of B cannot be 0. It can be at least greater than or equal to 2. Right? Okay. So every element generates here, therefore it should be order of C. Now what do I know? Order of B must divide order of A, but order of A is 12. That is 7 must divide 12. This is absurd. This is not possible. Therefore, B has to be zero element of Z7. That means any homomorphism F from Z12 are the only homomorphism F from Z12 to Z7 is the trivial homomorphism. Okay, pause, review, proceed. So that's a very, very important result. The result which you proved, order of f of a is a divisor of order of a if a is of finite order. That's a very, very powerful result. It's so easy proof, but I just wanted to impress upon you how significant the result is. That's why I gave. Remember, we will make use of this many times possibly in the course. Okay, and many of the questions which in interview or something they will ask, if they ask any such thing, the first thing you should think of this: can I use this result R of f of a as a divisor of R of a? That should be a very important trick, right? Okay, now let us look at few more things. So the next result I want to prove is this. I think the fifth result, let me change the color now. Fifth result is, let G to H be a homomorphism of groups. Then let's look at f of G. What is f of G? This is by definition set of all H in H, so that there is a G in G, so that H equal to f of G. So loosely teachers will write this as f of G as G varies over H. Collect all the images. Okay, G is in G, sorry. Right? Now notice that this is non-empty because identity belongs to this. Right? F of identity of G is identity of H, therefore E belongs to this. Therefore this is not empty. Right? And I claim this is a group. This is a subgroup. That is f of G is a subgroup of H. That proof is easy. Suppose let us say A, B belong to G. Sorry, let H1, H2 belong to f of G. Right? So I have to check whether H1 times H2 belong to H. And if H belong to f of G, okay, does H inverse belong to f of G? So I want to show this is a subgroup. What does that mean? Take two elements in this set, their product should also be in the set. And take any element, its inverse also should be in the set. Is this clear? Okay. Now what does it mean to say H1 belongs to f of G1? That means there is a G1. Let us say I for 1 less than I equal to 1 comma 2. There is a Gi in G, so that my Hi is f of Gi. Right? Therefore H1, H2 is f of G1, right, times f of G2. This is by definition. But since f is a group homomorphism, this object is nothing other than f of G1 times G2. So let G equal to G1 times G2. This is an element in capital G. Therefore, okay, there is a G in G, so that H1, H2 is f of G, namely f of G1, G2. Right? Therefore, this condition is satisfied. Okay. Now let's look at the second one. I think the second one also you know how to do that. Yeah. Suppose H belongs to H. There is a G in G, so that f of G equal to H. Right. Now I want to know H inverse. What is H inverse? That is f of G inverse. But does it remind you of something what you have proved earlier? That's the second result of today. That is nothing other than f of G inverse. Right. Therefore, this element is in G. Therefore, H inverse is the image of some element in G under F. Therefore, H inverse also belongs to H, F of G. Right? So, F of H is a, sorry, F of G is a subgroup of H. Okay, pause, review, proceed. Let me see whether I started the recording. Yes. Okay. So that's a subgroup. Now I can ask, since it's a subgroup, suppose, okay, I can ask two questions. Suppose G is cyclic. Say G equal to A. This, okay, one of the generators is A, right? Okay. Then what can I say about f of G? Let B equal to f of A, right? Then I want to claim this is nothing other than cyclic subgroup generated by B. This is our claim. This is almost obvious to do that because what is f of G? Okay, start with any element h in f of G. What does that mean? H must be f of G for some G in G. But any element G, how does it look like? It is look like a power k, right, for k some integer, because this is a cyclic group generated by A. Therefore, all the elements are a to the power n where is over z, right? Therefore it is f of a k, right? But we know what is f of a k, that is f of a power k. That means it is b power k, right? Therefore, you start with an arbitrary element h in f of g, then I said it is the power of b power k, right? Therefore, we conclude, and for all k in z, okay, b power k belong to f of g. Oh, because b power k is what? B power k is f of a power k, f of a power k. That is f of a power k. Please understand this logic. What I have shown is the following. I have proved f of g is contained in f of a power k as k varies over z. Now I want to prove this equality, right? So start with any element f of a power k, but from our third point we know it is f of a power k, right? Therefore that belongs to f of g, right? Therefore equality holds. Okay, is that clear? Therefore we know that if g is a, then f of g is f of a. It's a cyclic group generated by f of a. Okay, pause, review, proceed. Next question. Suppose g is abelian, right? Now I have f of g to h. Okay. Now you can ask whether, you cannot ask h is abelian, but I can ask f of g is abelian. Right? That is again clear because start with h1, h2 in f of g. That means hi is f of gi, right? Therefore h1, h2 is f of g1 into f of g2, but since f is a group homomorphism, f of g1 times g2, but since g is abelian, g1, g2 is same as f of g2, g1, but since f is a group homomorphism, it is f of g2 into f of g1, but that is h2 into h1. Therefore, for all h1, h2 in f of g, we proved h1, h2 equal to h2, h1. Therefore, g abelian implies f of g is abelian. Now, can you think of an obvious question as an application? I want you to think of an application. So there you can see my pattern. Whenever I prove some result, I immediately try to see, I can think of some situation where I can make use of that result. This is what you should learn, so that even if you don't find you will understand the statement of the result very well. That is the advantage. Okay. If you, so with practice, you will see you can always come up with some application. Maybe it easy, maybe not be easy, but you will get. Okay. But you if you don't get in the beginning, don't worry. Okay. Because when you try to find some application, you have to go back to the result, understand it better. So that is the advantage. Okay. So what is the thing I can think of here then? What does it say? It says if G is abelian, sorry, yeah, f of G must be abelian. So I can ask, suppose f is a map from G to H, it's onto, you, right? If onto meaning what? F of G must be all of it, right? Now can you think of a question? Yes. Suppose G is an abelian group, let us say, okay, say Z6 with, okay, 6 elements, cyclic group of 6 elements. Now look at H equal to S3. That is a permutation group on three numbers 1, 2, 3. That is also 6 elements, right? So I can see whether there exists an onto group homomorphism, right? Now you know the answer. So as an application, there exists no homomorphism F from Z6 homomorphism F from Z6 on to S3. Is the result clear? Because we know this is not abelian, whereas this is abelian. But if it is on to, that means f of Z6 must be S3. But this is abelian, this is non-abelian. So the answer is no. Okay. Pause. Review procedure. So assume there exists one such f. If there exists such a group homomorphism, f of Z6 must be S3. Since Z6 is abelian, in fact it's even cyclic, so yeah, my S3 must be cyclic. Okay. And in particular it's not abelian, but it's non-abelian. Is the result clear? Okay. Now let us look at one more application of the earlier result. This may be 8. Suppose I want to know whether there exists a map from Q plus onto Q star with multiplication. Okay, this is an identity group of rational numbers. This is multiplicative group of non-zero rational numbers. Suppose there is an onto. Right? This is the identity group, this is the multiplicative group. Okay, I want to know that there is a group homomorphism. This is of course a homomorphism. So I can solve the problem, but you should think how to think of such things. So I want to solve it. How do I think of it? Right? So on the codomain, it's a multiplication. Right? The codomain is a non-zero rational numbers is multiplication. Here it is. Right? Now, since the rational numbers, you want to make use of some property of rational numbers multiplication. How will you do that? There are a lot of things. One thing which comes to my mind is I know square root 2 is irrational, right? Therefore, I can say let me take b equal to 2 in the codomain, right? And then there should exist a pre-image, right? I want to deal with it. Suppose there exists okay. Therefore, there exists a rational number x in Q such that f of x equal to 2, right? Now, remember this x cannot be 0 because this is the additive group of rational numbers. Therefore, if x If x is 0, f of 0 will be 0, but f of 0 will be the identity element, which is 1 in q star, right? Which is not true. Therefore, x is not 0. Is this clear? Note that x is not equal to 0. Understand this proof? Right. Now let's look at x by 2. Okay. Then f of x by 2 plus x by 2, that is f of x, but that is equal to 2. Right. But what is f of x by 2 plus x by 2? Since f is a group homomorphism and the codomain is multiplicative, this is f of x by 2 times f of x by 2. Okay. Call this as something like r. Okay. Where is this r? This is r. This r is in q star. In particular, it's a rational number. Right. Therefore, this is r squared. So what you did? There exists a rational number q, so that its square is 2. Okay. This is observed. Therefore, no such onto homomorphism exists. Isn't the proof clear? Yeah. See, you should not think of such proofs as a tricky proof. Okay. You have to make use of that. Somehow I have to use multiplication. Somehow I have to use a rational number. Okay. Such things. For example, if I same question I ask from r addition to r star with the multiplication, then what will you think of? In r star I said, okay, all non-zero real numbers. Therefore, there exists a negative number, right? For example, if I minus 1, right? There exists minus 1. Therefore, if it's on 2, there is an x in r, so that f of x equal to minus 1. Do the same trick. F of x by 2 plus x by 2 must be equal to minus 1, but that is f of x by 2 squared equal to minus 1. But f of x by 2 is a real number whose square is minus 1. Nonsense, right? Just try to think of such things. So what I do look for? I look for something special about that which I can make use of, and multiplicative structure is what I looked at. In the first case, I made use of the fact square root 2 is irrational. In the second case, I said square of every real number is non-negative. See that? So please think. This is one of the problem solving techniques. Okay, you should not simply try to understand only the proof or solution given by a teacher. You should be able to think on your own. Okay, good. Now I want to investigate something else. Okay, usually such things are not done. Let's do that. See, this is a 10th one possibly. Suppose here from G to H is on to. That means you give me any Y in H, there exists an X in G, so that Y equal to Fx, right? And this X need not be unique. That is, there may exist, okay, X1, X2, so that F of X1 is B, it's also equal to F of X2. Right? It may happen, right? So what I want to know is maybe Y I used, right? Y. Okay. Since this is on to, for every Y, there exists pre-images. X in G, so that Y equal to Fx. Okay. I want to know, is there any kind of, can I characterize such pre-images? Let us look at. Suppose my f of x1, okay, let me write now only a and b. F of a equal to f of b equal to y. Okay, in H. A and b are in G, of course. Right? What does that mean? F of b into f of a inverse is identity, because both are y, right? But this I know what it is. It is f of b into f of a inverse. Remember, this is the identity element in H. But this, because group homomorphism, it's f of b a inverse equal to identity. Right? And notice that since I am assuming, if I assume A is not equal to B, then BA inverse is not identity, right? If there exists two distinct elements A and B in G, such that f of A equal to f of B equal to Y, okay, what I proved? Then f of B A inverse is identity. Then I claim B of A inverse is not identity, right? Because if it's identity, that means multiply by both sides by A, then I will have B equal to a contradiction, right? Therefore, it's not identity. So, what we proved is given a B in H, there exists at least two distinct elements such that f of A equal to f of B implies, okay, f of B A inverse is identity. And similarly, f of A inverse B is also identity, right? And that means there, that means in particular there exists X not equal to identity, that says Fx equal to identity. Please understand. Please understand this. So what I said is, if you start with the B in the codomain H, assume there exist two distinct pre-images A and B, such that f of A equal to f of B equal to, yeah, okay, I already used, okay, y in H, f of A equal to f of B equal to y in H. Then if A and B are distinct, then A inverse B is not identity. Therefore, I proved there exists a non-identity element X in G such that Fx equal to identity. Is that clear to you? Yeah. So we know f of identity is identity, but we are saying now there is a non-identity element X such that f of X is also identity. How did we get hold of it? Just because there exists one Y in the codomain H, but two distinct elements f of A equal to f of B equal to Y. Okay, right. So is the converse true? Okay, that is what we want to understand. Okay, that is, suppose there exists a non-identity element X such that Fx equal to identity. Okay, then I want to understand this phenomenon. So let us look at it carefully. We will do it. So it's best to make use of this word. Define kernel of F to be the set of X in G such that Fx equal to E. Okay. Now I want to characterize. So what we proved was, okay, if F is not 1, 1, then kernel of F, see, remember this EG will always be there. Kernel of F contains non-identity element. Yeah, it's a day full of interruptions. Okay, let us continue. The flow is affected. Yeah, right. So we want to prove, since, yeah, since the flow is affected, I think I will take a easy route. Let K equal to kernel of F. As I said, this is non-empty. Okay, right. I claim this is a subgroup K. Remember, it's an element subset of G. Therefore, I want to say it's a subgroup of G. Okay, why is that? Because suppose I have, okay, A and B in K, that means f of A is identity, f of B is identity. Now what is f of AB? F of AB is f of A times f of B, that is identity times identity. Therefore that is also in H. Therefore AB, when A and B are in K, that implies AB is in K. Similarly, let's look at f of A inverse. If A is in K, I have to check whether A inverse is in K. But f of A inverse we know is f of A inverse. But f of A is identity inverse. Therefore, it's identity. Therefore, A in K implies A is inverse K and identity is already in K. Therefore, K is a subgroup of G. Okay, pause, review, proceed. This is called the kernel. Okay, K is called the kernel of the homomorphism from G to H. Okay. So what I proved earlier can be summed up as a result. Okay. F from G to H, a group homomorphism. Then F is 1 1 if and only if kernel of F equal to singleton identity. This identity of G. Okay. One way I already proved, but to make it complete, I will prove both ways. Suppose F is 1 1, right? Then kernel of F, since yeah, okay, F of V is identity, right? Kernel of F, suppose there exists X in kernel of F, so that X is not equal to identity, but F of X equal to identity, but so is F of V. Therefore, F is not 1 1. Are you following? I claim F is, if this hypothesis, I have to prove kernel of F is trivial identity. Suppose not. That means suppose not, there is an X, okay, which is in the kernel of F, so that X is not equal to identity, but F of X is identity. But then Fx equal to Fe and X is not equal to E, that means F is not 1. So this contradiction shows kernel of F must be singleton E. Is that clear? So assume F is 1 1, claim, suppose kernel of F is singleton, this is the claim. Suppose false, there exists X in kernel of F, so that X is not equal to E. Since X is in kernel of F, that means Fx is identity, but so is F of E. Okay. Since F is 1 1, that means X is equal to E. But that's a contradiction because we assume X is not equal to E. Is that clear? Okay. So pause, review, proceed. Conversely, suppose kernel of F consists of only singleton. Then we want to prove F is 1 1. This is what we proved earlier. Do you remember? Because if F is not 1 1, okay, there exists x1, x2 in G, x1 not equal to x2, but fx1 equal to fx2, right? But then as we saw, f of x2, x1 inverse is identity. That means x2, x1 inverse is in kernel of F. But remember, x1 is not equal to x2. Since therefore, x2, x1 inverse is not identity, right? Therefore, there exists an element not identity which is in the kernel. That's a contradiction to our hypothesis, right? Therefore, F has to be 1 1. So this is again a proof by contradiction. If we want to prove F is 1 1, suppose not, there exists x1, x2, etc. Then what do I get? I get an element in the kernel of F which is not identity. That's a contradiction to my hypothesis. Okay. So pause, review, proceed. Is that okay? All right. Now, so we understood what is the kernel. Let us look at an example. Do you remember? F from Z plus and a group, then we always found some homomorphism. How did we do that? We fix an A in G and look at f of n equal to a power n. We know this is the group home. This is the homomorphism. Okay, this is seen in the earlier session. Right? So what is its kernel? Kernel of this map is set of integers n such that a to the power n f of a must be equal to identity. This is same as saying, sorry, f of a to the power n is identity. This is same as saying n f of a to the power n is identity. Yeah. Notice that 0 always belong to the kernel. Do you follow that? Yeah. Now, kernel of f is a subgroup of z plus, right? Now, there are two possibilities. All right, remember. Let us understand this. But we know any subgroup of z plus is of the form some multiple of z. Okay, there is a unique m greater than or equal to 0 so that it is m times z. Make sure that you understand this. Right, now the case 1, m is 0. If m is 0, what does it mean? Kernel of f is singleton 0. That is additive identity. That means f is 1 1. Right, from the earlier result. That means, okay, f of, if m is not equal to n, f of m is not equal to f of n. That means a power m is not equal to a power n, and for a, okay, for every n in z minus 0 not equal to 0, a power n is not equal to identity. Not equal to, sorry, identity. That means a is of infinite order. Order of a equal to infinity. Is that clear? So let us look at the kernel is a subgroup of Z. We understand what are all the subgroups of Z. They are of multiples of some integer m. So now the possibilities, if m is either 0 or some positive integer. If m is 0, what does it mean? A is of infinite order. Conversely, if a is of infinite order, the converse is also true. Conversely, order of a equal to infinity, then kernel of f equal to 0. Yeah, because f of a power n, sorry, f of n is a power n. For n not equal to 0, f of a power n is never identity. Therefore, kernel is 0. Is that clear? Therefore, what you have seen is kernel of f is 0 if and only if order of a is infinite. Pause, review, proceed. Now, can you make an obvious guess? Suppose kernel of f is some positive integer m, multiples of some positive integer m. What is your guess now? How many of you can guess? See, mathematics is this. You see the pattern, you build intuition, and you try to make a guess. The guess may be right, wrong. That's so still okay. I'm sure at least few of you would have guessed what should be. Yeah. Contrast with the last case, m must be order of a. Is it true? Let us check. Okay. Case 2, m is a natural number. Okay. Right. Now what does it mean? What is kernel of f? Kernel of f is set of integers m and n so that f of a power n is, sorry, f of n equal to a power n is identity. right? So this is a multiple of Z, and that means kernel of F, oh, okay, the singleton 0 is a proper subset contain non-zero element, therefore F is not 1 1, right? That means there exists some integer n, that means there exists some integer n such that A power n is identity. So I can as well assume that my n is natural number, okay, other than 0, a non-zero n. A power is identity. Because if A power n is identity, so is A power minus n, because A power minus n is A power n inverse, right? Therefore, I can assume there exists a natural number n such that A power n is identity. That means what? Therefore, as a first corollary, we conclude order of A is finite. Okay, pause, review, proceed. So what is that next we want to prove? We want to prove order of A is equal to m. Yeah. Now let us look at what is kernel of F. It said set of all n such that Fn, that is a to the power n is identity. That is, I am looking at all integers n such that a to the power n is identity. Okay, and there exists, as we saw, okay, I can assume there exists the set of all n natural numbers such that a to the power n is identity. That's non-trivial. This set is non-empty, right? You understand this? Okay, therefore there is a least element. That least element by our construction must be m. Therefore m is the order of A. Are you following? I'll quickly go through it. Okay, claim order of A is m. Yeah. So now let k be a natural number so that A power k is identity. Okay, let us do. Suppose order of A is finite, so let us assume order of A is k. Okay, there I have to prove k equal to m, right? Now that means A to the power k is identity. This implies, that is, f of k is identity. This implies k must be in kernel of f. But this implies k must be in m times z. This implies m must divide k. Remember, m, k are natural numbers. There if m has to divide k, right, that means m must be less than or equal to k, right? But k is the least positive integer. Remember, a to the power m is also identity. Okay, and k is the least positive integer, so that a to the power k is identity. But you are saying m is less than or equal to k, and a to the power m is also equal to identity. That means m equal to k. Okay, pause, review, proceed. Oh shit, sorry. Again, I did the usual goofing. Okay, we want to claim, okay, order of A equal to m. So let us assume order of A equal to k. Then what I know is a to the power k is identity. That means f of k must be equal to identity. What is a power k is f of k, right? That means k belongs to the kernel of f. But kernel of f is multiples of m. Therefore, k belongs to m. That means k must be a multiple of m. That means m must divide k. Remember, both are positive integers, natural number. Therefore, that means if m divides m, m must be less than or equal to k. But k is the least positive integer, so that a to the power k is identity. But since m belongs to kernel of f, that means f of m, that is a to the power m, is also identity, right? Are you following? Therefore, what do I know? K must be less than or equal to m, right? Therefore, k must divide m. That means k is less than or equal to m. Both these things put together says this. Okay, that's about it. So you can see we proved a lot of interesting results. Okay, about what are the main three results apart from the standard things? What are the standard things? F of identity is identity, f of a inverse is inverse of fa, and f of a power n is nth power of f of a. And from that, we did two things. Image of f, that is f of g, is a subgroup, and we define kernel f, that's a subgroup. Then the important thing is, if a is of finite order, f of e is also finite order, and the order of f of a is a divisor of the order of a. These are the important results we proved today. Okay, please review, go through it. I hope you enjoyed. We will meet again after about 10 days.